Okay, let's continue our discussion. This part, we are going to have a look of this EGM. EGM. EGM means extended GPU memory, and this EGM extends the GPU memory beyond the GPUs. Okay, this is very easy to understand. Don't make things difficult. Don't make things complex. It's very simple. Now, because if you look at this one, this is Grace Hopper super chip, and then you have the Hopper GPU here. This Hopper GPU can read and write to its own memory, and this Hopper GPU can read and write to the CPU memory from the same super chip. Okay, it has been shown by this blue line with an arrow, and this read and write has to go through this C2C NVLink. Okay, in a sense, the Hopper GPU's memory has been extended to cover the CPU memory. So it seems that right now the GPU has more than its own HBM3 memory. Its HBM3 memory has been extended. This is the meaning of extended GPU memory. There is no mystery here. Okay, this is within a Grace Hopper. Now you have a second Grace Hopper super chip. It's here. You have a second Grace Hopper super chip, and if you have an NVL32 system with Grace Hopper super chip, what you are going to have is a system with 32 Grace Hopper super chips, but the 32 Hopper GPUs will be interconnected by the NVLink network. Because the size of the system, the connection has to be done by using the NVLink switch. Okay, so the connection has to go through NVLink switch. This is the high-level architecture of an NVLink switch. It should be fitted into this square to pass the traffic. Okay. Then with this kind of NVLink network with NVLink switch, this Hopper GPU can access a remote Grace Hopper superchips GPU memory and CPU memory, as shown by this yellow line with an arrow and the blue line with an arrow. If you have to access the CPU memory, you have to go a little bit further. After you have gone through this NVLink network, you have to use this NVLink C2C to reach your final destination, which is the CPU memory. So anyway, this Hopper GPU have the capacity to read and write to the CPU and the GPU memory of a remote superchip. That means this Hopper GPU's memory has been extended to cover remote Grace Hopper CPU and GPU memory. This is the meaning of extended GPU memory. There is no mysteries here. It's just here. It's just here to explain that you have this kind of capacity for the GPUs to access more than its HBM memory. This is EGM. There is no mysteries here. Basically, the document is saying with EGM, GPU threads gain the capacity to access all available memory resources, including CPU attached memory and HBM, the GPU memory, over the NVLink switch fabric. This is the definition of EGM. This EGM is pretty much the result of multiple technical evolutions that we have discussed in section 5. Okay, after we have got all these technical evolutions in section 5, naturally we can have this kind of extended GPU memory. But we need to have a little bit more technical details regarding this EGM. Let's move on. In the document, Nvidia is saying that this EGM can be enabled in 3 platforms. Let's have a look at the first platform, which is single node, single GPU. Single GPU is easy to understand, is 1 GPU, and a single node means that the platform is just 1 node. Okay, the explanation is that you have to have an ARM-based CPU. You have to have a GPU, and between the GPU and the GPU, there must be a C2C link. And what's that? That's a Grace Hopper super chip. That's a Grace Hopper super chip exactly. So this is the type 1 system. And the type 1 system here, it means that the extended GPU means that this Hopper GPU can access its own memory, and it can also access the CPU's memory by going through this C2C NVLink. Okay, like this. It has a possibility to access the CPU memory. This is the meaning of this EGM. But we need to have a little bit more detail regarding now this. We pretty much can remove this one. I'm sorry, this is something should be here. Okay, if we need to understand a little bit more than the text. Here is that if you look at this CPU and the Hopper, at the very beginning of the GPU computing, the GPU are connected to the CPU by PCIe link. Okay, by PCIe link. And then in the very early days, you know what? You know the GPU cannot access the CPU memory, and the CPU cannot access the GPU memory. With some technical advancements, and later on, we found out that the GPU cannot access the CPU memory, but the CPU can access the GPU memory. Okay, there's a kind of asymmetric system we have discussed in section 3. Okay, now that's fine. Now, why it's like this? The reason is very simple, because to access a memory, you have the first step is to do the translation, the virtual address to physical address translation. And the GPU cannot access the system page table. Okay. So it cannot be the virtual address cannot be translated into the physical address. Okay, to be precise, you have a GPU page table which is hosted by the GPU. You have a system page table that's hosted by the CPU. Now, pretty much, I will call it the CPU page table. Okay, to access a piece of memory, the first step is to ask the page table to do the virtual address to physical address translation. And then the GPU can then use this physical address to read the data from the memory. Okay. But because this GPU cannot access the CPU page table, so if this GPU wants to access the CPU memory, the first step cannot be done because the virtual address to the physical address translation cannot be done by the GPU, and the GPU cannot access the CPU page table then that means the GPU cannot access the CPU memory. This was what happened with the very early generation GPU computing system. This is still something with these GPU computing systems with PCIe adapters. With this Grace Hopper superchip, things have been changed. Because here right now, if you look at this one, from the programmer's point of view, from the system, the user's point of view, there is a system-wide page table, and this page table is shared by the CPU and the GPU. So this time, right now, if this GPU want to access the CPU memory, if the Hopper GPU want to read or write to this CPU memory, things is okay right now, because right now the GPU can access the system page table, and the virtual address to physical address translation can be done by this page table. And then CPU and the GPU can access each other's memory plus their own memory. So there is a kind of symmetry here. The memory is shared. The CPU and GPU memory is unified, is shared. This is the programmer's point of view. This is the user's point of view. But we need to understand a little bit more than that, because here the real life implementation is a little bit more complicated than that. What really happened is this: you still have two page tables. You are going to have this CPU page table located in the CPU. Okay, you are going to have this GPU page table located in the GPU. Okay, but we have said that we have a unified system page table. Why is still located in the CPU and in the GPU? Yes, it is. We can understand this system page table is a logical page table, is a logical unified page table, but is a physically distributed page table. That means the page table the page table has been separated into two parts and distributed onto the CPU and the GPU. Okay, then there is something is not convenient here, is that each time the GPU want to access the CPU memory, it has to ask the CPU page table to do the translation of the virtual address to the physical address. And it is not practical. To make things more efficient and to make things fast, what Nvidia has done is that each side, let's cut it into two halves. In the GPU side, you have all this located in the GPU, inside this GPU. And there is a piece of cache which is going to be used to host the entries, the page table entries coming from CPU side. So you are going to have some entries comes from CPU side, which is a cache of some entries from this page table. Okay, the same is going to happen with this CPU. The CPU is going to have a cache, and in this cache, what you have is the page table entries, is a cache of the page table entries comes from GPU page table. So it's not a full copy of the page table, but it's a cache of some of the entries, which is going to cache the most often used entries and the recently used entries. So this is the concept of the cache. And in the end, what are going to find out that in the reality, what we have are still two page tables, but because these two page tables can cooperate each other, and each page table they even have a kind of an extension to host the cached entries. That makes the user feels they have a globally unified system page table. This is how the EGM works with this kind of superchip. And then let's move on. We need to bear in mind this picture, because in the following discussion, we are going to continue this concept. And in the second platform is this one. It's called single node multiple GPU. The definition is that a node is just a node. Single node means type 2 system. Single node means it's just one node and it's running just one instance of the operating system. And this system consists of fully connected 4 single node, single GPU platforms. And single node, single GPU platforms are type 1 system, are superchips. So type 2 system are a single node made of 4 with Hopper superchips. Okay, and here is exactly what we have. You have one superchip, you have another superchip, you have the third superchip, you have the fourth superchip, and then you have 4 fully connected type 1 system. You have 4 fully connected superchip. This is the type 2 system. Okay. For this system, things are a little bit interesting is that we still need to have a kind of logically unified system-wide page table from the user's point of view. System should be like this. You need to give them the feeling they have unified global system page table. And what happened and what we have explained is that in the previous section we have explained in reality what happened is that each one still has its own table, page table, and then the fact is that each one is going to have some cache to extend its own page table. And at the end, what you have is a kind of logically unified system-wide page table. But in reality, what you have are these are physically distributed multiple page tables, and globally the users, the programmer, they have the feeling they have a globally unified page table. And here the fully connected 4 single node, single GPU platforms mean that you have 4 CPUs. You have 4 CPUs. The 4 CPUs are fully connected, are connected this way in a kind of all-to-all fashion. Okay, this is for the CPU. It's the same thing for the GPU. Okay, if we change that to the GPUs are also connected the same way, and the connection are always NVLink. Between GPUs, they are NVLink C2C. Between CPUs, they are NVLink, the NVLink for CPU. And between the CPU and the GPU is also an NVLink C2C. So we have all-to-all connected CPUs and all-to-all connected GPUs. What have we have discussed here between the CPU and the GPU will be also true between the CPU and the GPU within a superchip. And it will be also true between the 4 GPUs. That means between the 4 GPUs, it works the same way as we have shown here. The difference is that here you have only 2 page tables, and here you have 4 page tables to work together. And that's this kind of scheme will also work with the 4 CPU page tables, and at the end you have 4 CPU page tables, you have 4 GPU page tables. At the end, by using this kind of a scheme plus this high bandwidth, high speed NVLink, okay, you have everything NVLink, and then from the user's point of view, from the programmer's point of view, what they have is a unified system-wide page table. Physically is distributed onto the 4 GPUs and the 4 CPUs, but they work together, and you have the logical unified system page table available for the programmer and for the user. Okay, maybe a little bit more technical details will help here. And notably, this a little bit technical detail is going to help our next discussion. Here it is. Okay, so we take 2 GPUs. We know the GPUs are interconnected each other by all-to-all. We have this NVLink C2C. Okay, we just take 2 of them. The 2 GPUs are interconnected, are connected to each other by using this NVLink to C2C. Okay, suppose this GPU want to read or write to the destination GPU. What's going to happen is that first, the GPU needs to ask this page table to do the translation from the virtual address to the physical address. But because this is reading or writing to the remote GPU, so there is the possibility there is no entry for this virtual address translation. So the way to have it work is that this GPU has to ask the other GPU to look after their page table. There is another page table. Let's draw it this way. Oh, the source GPU is going to ask the destination GPU to look up its page table and send the entry back to the source GPU. Okay, if this is the first time for the source GPU to read the destination or write to the destination. If this is not the first time, this entry should be already here in this cache. In this case, I mean, whatever the case, the first time or the second time, the translation will be done here. The translation will be done here, and is going to be send back to the memory management unit. Within this entry, we are going to have this physical address, of the destination GPU. So the source GPU is going to understand, okay, I'm going to get my data, I have to read to this physical address. The physical address I can get from this entry of this page table. And then I'm going to send my request. My use is NVLink. By sending my request, I'm going to ask this NVLink, okay, go and read the data from this physical address and give me back the data. And then the GPU, the network should be send a request to the destination GPU, and the destination GPU, they do need to ask to check this they do need to check this destination page table anymore, because that has been translated. It has already been done. What this destination GPU, the management unit, is going to ask the memory, the destination memory with this physical address to be read, data from that address to be read and send it back to the source CPU, again by this NVLink. This is what should have happened. And the other side, the other way around, is the same thing. If the destination GPU wants to read or write to the source GPU, is going to be the same story. The destination GPU first, they need to check the page table to do the translation, and then is going to send a request to the NVLink network with the destination, with the physical address that it wants to read to, and then send to the source GPU. The source GPU should be able to read from that physical address and send this data back to the requester. Okay, this is how it works. Here, the reason I want to discuss this here, because here things are going to get more complicated with the NVL72. Here, the point is that for this type 2 system, we have only single node. Single node means what? Means the source GPU and the destination GPU, they belong to the same node. Means there is only one shared address space. The request should be done by physical address. So the read, when the GPU want to read or write to the remote GPU, is going to ask to the NVLink network by attaching the physical address it want to read or write to. It want to read from or write to. So the physical address has to be used. And this NVLink connection, the setup will be done during the boot process. And the connection will be always there until the next boot. So this is for the NVLink C2C. I have put a cross here for this NVLink network, because this one is going to be discussed in the next slide for the third type of system. Okay.